Hello there, Data Rangers. Welcome to another episode of How to Algo. Today, we'll be tackling a classic problem known as the height checker. Imagine trying to organize a group photo with kids lined up by height, shortest to tallest. But here's the twist. They've all lined up randomly, and our challenge is to figure out how many of them aren't in the correct order by height. What seems like a simple real-life task becomes an interesting coding problem. Before we look at the ways you can tackle this situation, let's first talk about the constraints. Firstly, the number of elements in the heights array must be between 1 and n. N represents the maximum number of elements the array can contain. This means that the array cannot be empty and must contain at least one element, but no more than n elements. Secondly, each height value in the array must fall within the range from 1 to the maximum value present in the array. This ensures that every height is a positive integer and within the bounds defined by the maximum height in the list. First up, let's start with the straightforward method, using sorting of the heights array. This method involves sorting the heights and comparing them to the original array to see how many positions are out of order. In this case, 3 are out of order. For example, consider an array of heights. After sorting, the array will now look like this. Now, if we compare the two arrays, we can observe that indices 2, 4, and 5 are out of order. Let us now take a look at the pseudocode. We first take the heights array and copy the elements to the array clone, as we don't want to make a change to the original array. We then sort the clone array, just like lining up kids from the shortest to the tallest. Then, initialize an integer variable result to 0. This keeps track of elements which are out of place. Now, we simply check each position and see if the sorted height matches the original. If not, it counts as an out-of-order kid. Simple, right? It's just like counting how many kids snuck out of line when the teacher wasn't looking. The time complexity of this algorithm is big O of n log n, because we sort the clone. The space complexity of this algorithm is big O of n, because we create a copy of the original array, hence using n space. But simple isn't always fast. This method isn't the quickest, especially with a lot of kids or data. Let's see the optimized approach using a frequency array to determine the students those are out of order. Here's the pseudocode for this method. We create a variable called result and set it to 0. This will be used to count how many elements are out of order. Next, we create another variable called current height and set it to 0. This variable will help us track the height we are currently expecting as we reconstruct the correct order. Here, we create an array called frequency with n slots, n being the maximum number of elements the array can contain. It varies depending on the constraints given, in this case 5, and initialize all of them to 0. This array will be used to count how many elements there are of each height. We loop through each height in the array, and for each height, we increase the corresponding index in the frequency array by 1. This counts how many elements there are of each height. Now, we start another loop that goes through each position in the heights array from the beginning to the end. Inside this loop, we have another loop that checks if the current height we are looking for, indicated by current height, has any elements left to place. If frequency of current height is 0, it means there are no more elements of that height to place, so we move to the next height by increasing the current height. Now, the current height is 1. Since frequency of 1 is 3, there are elements of height 1 to place. We now start looping through the heights array. At index 0, height is 1, current height is 1, and frequency of 1 is not 0. There is no mismatch. The current height is equal to the height at index 0. Therefore, we skip this condition and decrease frequency of 1. At index 1, height is 1, current height is 1, and frequency of 1 is not 0. There is no mismatch. The current height is equal to the height at index 1. Therefore, we skip this condition and decrease the frequency of 1. At index 2, height is 4, current height is 1, but the current height is not equal to the height at index 2. We increment result as there is mismatch. Frequency of 4 remains 1. At index 3, the height is 2, current height is 1, but again the current height is not equal to the height at index 3. We increment result as their mismatch. The frequency of 2 remains 1. At index 4, height is 1, current height is 1, and frequency of 1 is not 0. There is no mismatch. The current height is equal to the height at index 4. We skip this condition and decrease frequency of 1. At index 5, height is 3, current height is 1, and frequency of 1 is 0. The current height is not equal to the height at index 5. Increment result as there is mismatch. Frequency of 3 remains 1. After iterating through the array, the result is 3, indicating that there are 3 elements out of order. And we're done. The time complexity of this algorithm is big O of n. Despite having 2 loops, the outer loop runs for the number of elements, and the inner loop is bounded by a constant value. If there wasn't such a constraint, the time complexity would be big O of n squared. The space complexity of this algorithm is big O of n for the same reason. The extra space used is the frequency array of size n, and there you have it. By using the counting sort method, we achieve a more efficient solution both in terms of time and space complexity. And that's it for today's episode of How to Algo. Now you know 2 ways to tackle the height checker problem: a straightforward sort and compare method, and a more efficient counting sort approach. Stay tuned for more such videos on how to algo. See you in the next video.